Okay, welcome back. We spent Monday talking, we spent Monday talking about electric charge and just the nature of charge in general. Today, we're going to talk about how to give objects net charges so that they have more electrons than protons or vice versa. So, we mentioned this the other day, how do charges move around? Typically, only negative charges, or remember which one the negative charges are, those are the electrons, can move around. Okay? Typically, the positive charges, the protons, they stay in place. And the reason that they stay in place is because they are kind of locked in the nucleus. It's very, very hard for one of them to escape the nucleus. Okay? Very, very difficult to do. You can see a random proton floating around, but typically it's the electrons that are going to be able to move. We're going to assume when we do all these diagrams that we're about to do, we're going to assume that only the negative charges are moving. So, when I say that electrons can move, that's really only true. Well, it is true. The electrons can move around, but the extent to which they move around is different for different objects. Some objects allow their electrons to move around wherever they want to in an object. These objects, as you probably learned back in elementary or middle school, are known as conductors. It's very easy for the electrons to move around. The best conductors are usually metals. Some liquids like water are also good conductors, especially if they're ionized. But metals are very good conductors. That's why we make wires out of metal. In a conductor, electrons will always try to spread out so that they are as far away from each other as possible. And why do they want to do that? Why do they want to be as far away from each other as possible? Well, think about it. Electrons, as you know, are negative. So if you put two electrons near each other, what happens when you have two like charges next to each other? They will try to repel. And if you have a whole bunch of them, they will spread out as far as they can within the confines of that object. So, for instance, if you, let's say, we've got two little objects here, represented by these circles. We're going to do a before and after. Let's say in some certain case, you have a bunch of electrons that appear here, and they're like this. They're on the right-hand side of the object. Again, I just did minus signs for negatives for the electrons. As long as nothing else influences them, what's going to happen is that these charges are going to spread out if there's no other effects on them. Okay, so if they all started right here, let's say they all just kind of, and this isn't really what would happen, but they started right there. After a while, they will have moved so that they are as spread out as possible. Now, one thing I want you to note is how many charges I used. Okay, I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 charges here. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 charges in this picture. When I'm asking you to draw these pictures, I'm going to ask you to make sure that if you start with a certain number of charges, that you end with that same number of charges as long as none have left the situation. Don't draw one charge over here and then 6 over here. I'm going to ask you, hey, where'd those other 6 charges come from? You didn't show me that they're being introduced to the problem. So when you're drawing these diagrams, I need you to be thinking. Okay, you can draw as many charges as you want, but it's got to be consistent between pictures. So in conductors, charges spread out to be as far away from each other as possible. On the other hand, we also have things called insulators. This is a different type of object. Insulators are materials that impede the free movement of electrons. Electrons can't move as easily in an insulator as they can in a conductor. A few good examples of insulators. Think about what we put over wires. We usually put rubber coatings over them so that the charges can't leak out of the wire. Wood is actually not a very good conductor. Wood's a pretty good insulator. And air is also a fairly good insulator. That's why you have to be really close to something in order to get shocked by it. Imagine if air was a good conductor. You'd get shocked by things by standing very far away from them. That wouldn't be very good. Okay. All objects have the ability to become polarized. And this is a process that happens when electrons move around inside an object. And this happens to both conductors and insulators, just to different extents. Now, electrons move around inside an object. That is what polarization is called. Okay? This does not mean that any charges actually leave the object. The electrons simply move around on the inside of it. Let me give you an example of polarization, a charged balloon approaching a metal wall. So let's say we had a balloon. Okay, here's our balloon. It has, looks like 8 negative charges, and it is going near this wall. And for the sake of simplicity, I'm going to draw 8 charges on the wall too, but the wall is, let's go with neutral for right now. How do we know the wall is neutral? It has the same number of positive charges as negative charges. And since it's a metal wall, we know that it must be a conductor. What happens if I bring that balloon close, I drew it bigger, to the metal wall? Well, what you would see happening here, as that negative balloon goes towards the negatively charged balloon goes towards the wall, since it's a metal wall, these electrons that I'm representing with negative charges, they're not fixed. They can move. And if more negatives come along towards them, what do you think they're going to do? They're going to want to get away from those negative charges in the balloon. So this negative right here and this negative right here, they're going to leave. They're going to try and get as far away from that balloon as possible. The positives aren't going to leave. The positives are going to stay in place. But those negatives, they can't leave the object. But what are they going to do? They're going to get as far away as possible. So now they've moved down over to the other side to get away from the balloon. In addition, the charges on the balloon now look at this side of the wall. This side of the wall now has a positive charge. That's going to attract those negatives in the balloon. So what you see here is we have something that has been polarized, okay? The charges have moved inside the balloon, giving it a definite negative side. Over here, there's not as many electrons. And let me make this point. I'm not saying every single electron moves over to the right side of the balloon, but a lot of them will. This right side of the balloon now has more electrons. It's a more negative side of the balloon. This side of the balloon, where some of those electrons left, that's now a little bit positive. That's what polarization means. It means taking one object and splitting up the charges so that the object has a distinct positive side and a negative side. It's very easy to see here with the wall. The left-hand side, there's only positive charges left there because a lot of those negative charges have moved to the other side. So we've got a positive side to the wall and a negative side to the wall now. So what we say is that the wall is polarized. The charges have separated, but there is no transfer of charge from one object to the next. No object gained or lost charge. The charges simply moved around inside the object. And what this leaves us with is an object that has two distinct halves. One half of this wall is now positive, one half is negative, but overall, the wall still has equal numbers of positives and negatives, equal numbers of protons and electrons. So the wall itself is actually still neutral. Okay? That's called polarization. What I want to do is I want to show you a little diagram or a little simulation that I have, and the website that I'm going to for this is called the Physics Classroom. It's a really, really good resource, I think, especially for this unit in particular. So let me get this set up, I think, the way I want it to. Let's see here. I'll show you in just a sec. Okay. So, all right. So in this simulation, you see we have a balloon. Balloons are made out of some sort of rubbery, latexy material. That's typically not a very good conductor, okay? So we've got this balloon. The charges are actually very, very kind of concentrated right here because they can't really move around all that well. Over here we have two metal bars, one here and one here. If I bring one of the metal bars close to the balloon, look what happens to the negative charges. The negative charges have gone away from that balloon. What we've done is we polarized this object. This object is now polarized because it has a distinct half. This half is more negative. This half is more positive. Okay? The balloon has polarized the metal bar. And you'll notice, and even the other one is polarized to some extent, it's got kind of like a negative top half and a positive bottom half because the negative charges, the electrons in this balloon's negatively charged, are repelling these negative charges up here. Let's see, what was I going to say? Okay, so yeah, we've got so the key thing here is we have not moved any charges from one object to the next. The balloon hasn't touched the metal bar. If we were to count the number of charges, we haven't given any extra negative charges to the metal bar. We haven't taken any away. And you'll notice that those positive charges are just staying in place. Watch what happens when I take the balloon away. Okay, the negatives are all spread out, or all kind of clustered on that metal bar over on the left-hand side. If I remove the balloon, look what happens. The charges go and they spread out again. Now there's just a little error with the coding here. This, we should have this charge really over here, so that's a complete spread out. But oh, look at the top one. Everything is spread out perfectly, okay? These are conductors. Charges spread out to be as far away from each other as possible. If I bring the balloon back, we get polarization again, okay? This is the idea with polarization. We're not giving any more charges to either object. All we're doing is we're simply moving the charges within the object, creating specific positive and negative halves. That's what polarization is. I've got one more thing to talk about in this video, and that would be how we create a charge. How to actually, polarization is not giving an object a certain charge, it's simply splitting up the charges. We want to talk now about the 3 ways that you can give an object a net charge. Okay, this can happen in 3 different ways. The first, the most common, is called charging by friction. All it takes to do this, rub 2 objects together. Okay? One of the objects will automatically grab electrons from the other object, depending on the 2 types of objects that you have. We don't have to know which object grabs from which, but it's based on the type of material that you have. The key here, and we alluded to this on the homework and in the notes the other day, is that the number of electrons gained by one object is equal to the number lost by the other object. And this is known as the law of conservation of charge. And like I said, we alluded to this the other day when we talked about, when we did the example with the comb going through the person's hair. If the comb took 2 electrons, if the comb gained 2 electrons from the hair, that means the hair lost those 2 electrons. That's conservation of charge. You cannot create or destroy charge. So let me show you an example, a little sketch. We're going to practice drawing diagrams again. Let's say that this is just a neutral rubber stick. And that neutral rubber stick, we know it's neutral because it has even numbers of positive and negative charges. In this case, I like to do 4 of each. That's not a rule, but that's just kind of what I like to do. Let's say we also have a neutral piece of fur. Normal fur, like you'd find animal fur. Back in the room, I have a lot of this, and we would actually do a lab on this, but obviously that's a little bit impossible right now. And we know that this is neutral because, again, equal numbers of positive and negative charges. Well, what happens if we rub the stick with the fur? Okay, essentially, if we rub those 2 together, there's going to be some friction there, and that friction is going to allow charges from one object to go to the other one. What ends up happening is you end up with a stick that is now negatively charged. How do we know it's negatively charged? Because now there are more negative charges than positive charges. Oop, I missed one. Put that one on the end. Okay. How many more? Well, I still have my 4 positive charges. However, I now have 1, 2, 3, 4, 5, 6 negative charges. What does that mean for my fur? Well, if this gained 2 electrons, this had to lose 2 electrons. Notice I'm keeping the positives in the exact same spot as well. This fur just lost 2 electrons. So now I show it as having positively charged fur. The charge on this would be negative 2e. The charge on this would be plus 2e. Okay? That's how charging by friction works. Whatever one object loses in electrons, the other one gains in electrons. The one that's gaining electrons, remember, becomes negative. The one that loses the electrons becomes positive. When we come back, I'll probably have a couple more little simulations to show you, and I'll also talk about the 2 other methods of charging.